Well, we're about to start in about a minute.
Thank you for coming. I had to come.
Well, thank you for coming this afternoon. Before we start, we're to ask you to be aware of our exit signs to the doors in case we need to leave the room on short notice. Those that are on the internet watching today's broadcast, we strongly advise that if you're going to be sending questions in for the Q&A, that you do it at earliest possible opportunity so we can have time to take it. So with that, Wanju.
Good afternoon. Welcome to the seminar. Dr. Bressinger is the Indoor Environmental Group Leader in the Energy Analysis and Environmental Impact Division, and also a Principal Investigator in the Whole Building Systems Department at Lawrence Berkeley National Laboratory. Dr. Singer has conducted numerous research projects related to air pollutant sources, physical-chemical processes, and pollutant exposures in both outdoor and indoor environment. Dr. Singer's recent focus has been on indoor environmental quality and risk reduction in high-performance homes. We are very happy to have him and also his staff to conduct this in-home exposure study for us. With that, please welcome Dr. Singer.
Thank you. Great. Well, thank you very much for the opportunity to be here today. And thank you to the Air Resources Board for sponsoring and supporting this research, which we feel is very important, and we're glad to see the ARB's interest in this as well. And please do send questions. It's much more fun at the end to know what's on your mind having seen this presentation. I'm going to shoot for 45 to 50 minutes. I'm going to try to not rush through, and then that should leave some time for questions. So of course the statements and the conclusions in this presentation are not necessarily those of the Air Resources Board. The mention of commercial products, their source, or their use in connection with material reported herein is not to be construed as actual or implied endorsement of such products, of course. So obviously a study like this doesn't happen without a lot of people contributing. I had really great colleagues at LBL, Tosh Hochi, Brendan Less, Melissa London, Marion Russell, Chris Stratton. I guess I didn't actually indicate at the opening slide my close collaborators on this project at LBL, Woody Delp and Doug Black, who did a lot of that real hands-on work. Woody did amazing analysis, preparation of presentation materials, et cetera. Really good visuals. And then Ian Walker, who is an expert on HVAC and filtration, and Ugo de Stelyaats, who is an expert on the VOC removal technologies. Getting back to the others who helped balance point home performance, Gavin Healy and Dan Perunco, they were the wizards who helped us to actually make this happen in a real home. At the ARB, I want to thank the contract managers in the group of Peggy, Mike Gabor, Zoe Zhang, and Youngju. Thank you very much for your excellent contract management. Frank Hams of IQ Air provided a prototype for us to test, which was turns out to be a System C, which you'll see here in a few minutes. And then we had a really great technical advisory committee as well. So what's the background or context here? Well, in general, homes can be designed to reduce our exposure to air pollutants. We spend a lot of time indoors, and a lot of the time that we spend indoors is in our homes. Many California homes are in places that are impacted by outdoor air pollution. And of course, we have indoor sources of air pollution as well. Turns out that the pollutant loss as air enters into the home and also as air is in the home can reduce our exposure to outdoor air pollutants relative to what it would be outdoors. That's great. The home is protective of outdoor air pollutants in a lot of cases. And we can engineer our ventilation and filtration or air cleaning systems to improve that protection. Now that's the broad context. There's some specific context, which is that for energy efficiency purposes, California building code requires homes to be built tighter, makes it easier to manage the thermal conditioning of the outdoor air if you can control your outdoor air coming in. And that requires us to add mechanical ventilation. And before this study, there wasn't a lot of attention paid to how the ventilation system itself affects your exposure to outdoor air pollutants. And the Air Resources Board was concerned that some of these mechanical ventilation systems could actually have detrimental effects or be not as protective as other ventilation systems. They were interested in how you engineer the whole thing of the ventilation and the filtration and air cleaning systems to achieve these potential reductions in protection from, or the improvements in protection from outdoor particles and other pollutants. So the study objectives, by far the most important was to quantify the effectiveness of the ventilation and filtration systems at reducing in-home exposures to outdoor air pollutants. There was a focus on PM₂.₅, so this is the particulate matter smaller than 2.5 microns, this is what's regulated. Also ultrafine particles, there aren't regulations for ultrafine particles, but there's more and more evidence that these are particularly harmful. And these are particles that are smaller than 0.1 microns, so they're much smaller than the 2.5, smaller than 0.1. And the feature of these particles is that they can move through barriers in the body that stop bigger particles. So these are exogenous or outside materials that get into your body and can move into places that other things can't get to. And then we're also very interested in diesel particulate matter. There's a metric that we use for that called black carbon. So it's kind of how dark, the diesel is obviously dark. Diesel particulate matter, you can see it on your windows, for example, or depositing on old buildings. So that's another important pollutant that we're concerned about. There's a secondary focus on ozone, on volatile organic compounds and indoor generated particles. And then the goal is to identify compatible low energy systems that are suitable to California and to quantify the energy use of these systems relative to a reference system. And so we're looking at the performance for pollutant protection and the performance for energy. Again, some context. A lot of great outdoor air pollution studies happened by the Air Resources Board. We're moving indoors, so it's helpful to understand how air moves around and gets into buildings. Basically, a conventional house, air, if you close the windows, if you open the windows, of course, you're trying to make your inside look like outside, so that's not as interesting to us, okay? It's great, I like to open my windows, but if you're trying to protect yourself from the outside, windows are closed. Air traditionally has gotten into your house through what we call infiltration, so kind of moving through cracks and gaps in the building shell. That's one way that's the way the air gets in, and then air moves around the house through sort of natural convective forces, but also through your air handling unit or your forced air unit. So that's your air conditioner and heater that pulls air from one place, thermally conditions it, and redistributes it. And you can see that here. So the red arrow is the warm air coming up into the return. The forced air unit is up in the attic. It's a very common configuration in California. Sometimes they're in a garage, sometimes they're in a crawl space, but most commonly in the attic. And then it gets redistributed. In this case, we show blue for cooling. Now, as you make your home more energy efficient by air sealing, you see that little inset of the red. That's going to cut down on the infiltration, and it's going to make more tortuous paths for the air to get into your home. So there's going to be less of it, and it's going to have to go through a longer obstacle-ridden pathway. And as you might guess, that means it's going to bounce into more things along the way, so it's going to remove some of the pollutants. Certainly ozone and particles will be removed, and NO2 to some extent as well, as air passes through all these narrow gaps and cracks. Airtight homes have to be ventilated to make sure that they get enough exchange so that the indoor sources, for example, all the VOCs that are emitted from materials don't get too high. There's three basic ways you can ventilate. One is an exhaust ventilation system where you suck air out of the house, and then you rely on air coming in through all those gaps and cracks. The other is that you push air into the house, you supply it, and then air gets pushed out through all those cracks and gaps. And the third is a balance system where you both push it in and supply it, and you pull it out through exhaust fans. And we looked at all three of those. So now that's the ventilation part. Now the air cleaning part. Well, there's some different options. We're going to start with particles or pollutants that are already inside. So if you have pollutants inside your home, you can remove them using your forced air unit, right? This is a big fan that moves air through a device, right, through your thermal conditioning system. You can put some kind of air cleaning system or a particle filter there. If you do that and you do nothing else, then whenever your thermally conditioning, you're heating or cooling, you get some benefit. Great, it's kind of like a free benefit, right? You were cooling and heating anyway, so you remove some pollutants along the way. The next thing you can do is you can now operate your forced air unit specifically to do air cleaning. Okay, so now you're using more energy because you wouldn't otherwise be operating it, but you're getting a lot more benefit. And you could also theoretically use room air cleaners. ARB has sponsored lots of studies with room air cleaners. That wasn't the focus of this study. This was more on things that were installed as permanent equipment in the house. Now the outdoor pollutants. Well, you can filter or you can clean the outdoor pollutants from the inside. So after the air comes in, you have all those same options that you had up above using your forced air unit, et cetera. You could put some kind of filtration or air cleaning on the supply ventilation. So you put a filter as you bring air in, you push air into the house, you push it through a filter. And then when you use exhaust ventilation, your house becomes your filter. So as I said, as the air moves through all those cracks and gaps, some amount of pollutant removal happens. So your tight envelope acts like a filter, and we'll see that actually can be pretty effective as well. So I mentioned filter effectiveness. This next slide actually shows three important concepts. So the first is that filters are not all created equal. I think we sort of all know that intuitively. There are different systems that are available for ranking or rating filters. In this project, we use the minimum efficiency reporting value, or MERV rating. And I show here a couple of examples. If you go to your hardware store and buy a really cheap filter, it's going to be a MERV 4. If you buy something that is a little bit better and has some performance, it might be a MERV 7 or MERV 8. We call these medium efficiency when you get to kind of MERV 11, 12, 13, and then high efficiency gets up to MERV 16, and you can have HEPA filters, which is a different designation. So that's the first. Filter performance varies, and we use these MERV ratings. The second is that the performance actually increases when the filters load. And to understand that, I have two plots here, and the plots introduce the third concept, which is particle size matters. So across the bottom, you see particle sizes on the x-axis, and it goes from 0.01 microns up to 10 microns, right? We have a PM₂ standard as well. And you see in both cases, what we're looking at here is the filter efficiency, so it's what the percentage of the particles that are removed when air is moved through the filter. So 100% is really good, 0% is really bad, and you see most of them are somewhere in the middle. And then you see both filters have this characteristic shape where they do better at the bigger particles, and then they take a dip as the particles get smaller, right? So if you look at the MERV 12, for example, when it's new, there's the bottom of that little dip is at about 50%, at 45 to 50%, and that's right around 0.3 microns. So these are the hardest particles to remove, these 0.3 micron particles. And then in this filter, it gets a little bit better as you get to smaller particles. The MERV 7 dips a little bit lower. And then the third concept is that the loaded filters, when you start loading filters with dust, then the performance actually improves. And that's because, is a question? We'll take questions at the end, I think. Okay. I usually like to take them now, but since people are online, they can't do that. So the performance improves. Now, that doesn't mean you should load up your filters and leave them in there forever, because there are negative consequences of having filters that get too overloaded. Airflow, you build up pressure, so it takes more energy or power to push air through it. And if you, depending on the kind of fan you use, you either use more energy to push the same amount of air through, or you push less air through, and then as you push less air through, then your heating and cooling system works less efficiently. And then, so that has implications too. So some amount is good. What you're seeing here in terms of the improvement is something that would be kind of middle to end of life of the filter, okay? So the performance of the filter would start kind of when they're new and would get up to the point where they're about what's shown here, and then this is roughly where you'd be changing your filter, because at some point your pressure would get too high. So what did we test? Well, we looked at, again, ventilation and enhanced pollutant removal systems. We designated a reference system, which is what we think is the most commonly found system in California. And then we tested 7 other systems with enhanced pollutant removal. We looked at exhaust supply and balanced ventilation systems. We looked at different levels of particle filtration from MERV 8 to MERV 13 on the supply ventilation, from MERV 4 to MERV 16, or an electrostatic precipitator on the forced air unit. And then we looked at a HEPA filter on the bypass for the forced air unit. You don't put it in line because it's too much pressure drop for all of the flow. So you pull some flow off, and I'll show you a picture of that. And then we also did limited experiments with some portable air cleaners that had HEPA filters. For VOC removal, we looked at activated carbon as by far the most common technology. We also looked at a chemisorbent and at a room temperature catalyst. The basic approach is really simple. In concept, at least. In practice, it was not so simple. So the basic approach was we wanted to install all these systems in the same house where they were seeing basically the same outdoor conditions. So we found a house, that's, and I'll show you in a minute, outside of Sacramento. Actually, yes, it's in Sacramento. And it's impacted by outdoor air pollution. We installed all of these systems in the same house, and we set it up in a way that we could switch between the systems relatively easily. So we run a system for a week, run the next system for a week, next system for a week. And we did this in both summer season and in fall-winter season. The reason we do that is because the particles and the outdoor pollutants are different between summer and winter, so we wanted to get both. We measured air pollutant removal and energy. We evaluated, we also did limited testing to look at how these systems did for an indoor source. So we generated particles by a scripted cooking activity that we'd used for previous experiments. And then we measured the particle levels and the other pollutant levels inside and outside. Key metrics here are the indoor to outdoor ratio. So a lower indoor to outdoor ratio is a good thing. And then the percent reduction. And that, for the outdoor particles, it's a percent reduction relative to what's outdoors at the same time. And for the indoor particles, it's a percent reduction compared to what would happen if you don't operate any of your systems. And then we estimated annual energy use. So I'm going to just step through the systems. You'll see 8 of these pictures. I'll go over the important features of each one. So at the right-hand side, you're looking at a schematic of the forced air unit. That's the big thing in the middle. So there's air being pulled from the return. The return grill might be in your hallway or a big common room or a stairwell. Then it conditions the air and it redistributes it to all those grills that you see around your house. And the reference system is this basic system with a cheap MERV 4 filter and exhaust fan providing their ventilation. And the exhaust fan will very often be a bath fan or a laundry room fan that has a high setting when you need a higher flow and a continuous setting for ventilation. The most basic variant of that would be a supply ventilation system. And here we looked at a supply ventilation with a MERV 13 filter, and we have it continuously pushing air into the return side of the air handler or in the forced air unit, the FAU. When the FAU is on, it distributes that around. When the FAU is not on, it probably dumps it out through the return. That's the lowest resistance pathway. Next system, system B, was that same system, but we added an electrostatic precipitator that just operates on the thermostat. So this is kind of the no extra energy cost for the electrostatic precipitator. It's a small extra energy cost because it only operates when you're otherwise heating and cooling. And we actually saw this in our data, and I'll show you where you see that in the data. Next system was a little bit more sophisticated supply system. Here we're supplying through an independent system, so it's not going through the forced air ductwork, but we don't want to dump completely unconditioned air into the house, right? Because if you're standing by that, it's going to be uncomfortable with the hot air in the summer, the cold air in the winter. So we mix it's about 2/3, 1/3. 2/3 of indoor air with the supply air, so it tempers that supply air, and then you don't really notice the temperature difference, and it allows you to do much more efficient air movement because you're only moving air through this small amount of air, and you can put a really good filter there. So we had this filter it's a MERV 16 filter with the catalyst technology. The next system, here we're stepping up to a MERV 16 filter. It's still a supply system. We're operating this a little differently. Instead of continuously, we're operating it intermittently because we have to use the forced air system, which uses a lot of energy. It's a high power unit. And we have MERV 16 filtration plus the chemisorbent, and it's operating for 20 minutes out of every hour. The amount of ventilation air that's provided in all these systems is the same, plus or minus, within the margins of error. But basically, the idea is to bring the same amount of outdoor air in, and we measured air exchange rates as well and found that that was basically true. System E, we're going back to the exhaust ventilation, and in this case, we're putting a MERV 13 filter on the return. So this is also a very simple step up from what is currently the most common system. This is just putting a better filter on the system you have and adding a timer to turn it on for 20 minutes out of every hour. Okay, so this is something that actually is an adjustment that's you could retrofit existing homes to do this pretty easily. System F is looking a little bit toward the future. We expect to see more of these quote-unquote mini-split heat pumps. What we looked at here is a ducted system. So this would be something you might put up in a hallway, a central hallway, with short duct runs to the bedrooms and a return, right there in the hallway. And so it is a forced air system in the sense we're pushing air around the house, but it's much, much less ductwork than we would have in the conventional system. And the other feature of this is that it has a variable speed fan. So we operated this one, we put a MERV 13 filter on it, and we built a special filter box with a low pressure inlet, and we operated it continuously at a low speed. One of the features of these mini split units is that they have ECM motors, which have very good efficiency of part load. So you actually, the amount of power you use, watts per cubic foot of air movement, is better at a lower speed than a higher speed. So in this case, to give you some, and I have numbers at the bottom that I haven't really been mentioning, but the forced air unit was a 1200 watt fan, okay? So even if you're using it a third of the time, it's 400 watt hours for every hour. This one is 100 watts at the low speed, so it's only a fourth of the energy to move the air as the conventional forced air unit. And if we could, we probably could have gotten away with running it even at a lower speed with less energy. The last system was a little, we call it the Cadillac system. So it has a heat recovery ventilator for your ventilation. So you're getting some heat recovery for energy efficiency. And that dumps into the return. And then it has a HEPA bypass on the system plus a carbon filter. And that's operated again on that 2060 intermittent cycle. And then the last one, again, was just kind of throw in at the very end. We had an extra week in the house, and that was looking at that reference system with a couple of portable units just to see how that would compare. Because again, for somebody who doesn't have the money to retrofit their system, this is an option, so we just wanted an apples to apples to see what that does. Actually, I want to come back here. Yeah, that just shows where the two portable units were placed. So the test house, this was about 300 meters downwind of I-80, so it's impacted by the freeway, not next to the freeway, but we're still seeing particles, et cetera, from the freeway. Built 2006, 1,200 square foot house, 3 bedrooms, 2 bath, 1 story, slab foundation, and the forced air unit is in the attic. Lots and lots and lots and lots of homes in California that look similar to this, maybe a little bigger, but lots of homes built with this basic setup. We did a smaller home because it's easier to get it well mixed, basically. This is the layout, so you see the garage. The equipment was put in the master bedroom. I think I have, in the next slide I show here. So you see the cutout of the house on the right. The sampling locations, outdoors, we sampled just above the roof line, and we sampled right next to the place where we're bringing air into the house from outdoors for the supply ventilation systems, okay? We're presuming the air around the house was all pretty similar in terms of outdoor pollutants. Obviously for the exhaust system, air was coming in from lots of places, so we have to assume it's similar to what we're measuring up top there. And then for the indoor location, actually that asterisk got moved a little bit. It's just slightly down. It's in that central hallway though, basically, right in the middle of the house. This is a beautiful find. When we found this house, we were so excited. The indoor and outdoor sampling lines were exactly the same, so that gave us confidence that we were making a valid comparison. We had a whole suite of instruments. We were measuring size resolved particles down to 6 nanometers and up to 2.5 microns. And we had different size cuts. We also were measuring black carbon using an ethylometer. We used a dust track to measure an estimate of PM2.5 through light scattering. And then we actually calculated PM2.5 from the size resolved particles and used that to estimate PM2.5. We didn't do mass or gravimetric measurements of PM2.5. They're much more expensive, and the cost of the project would have increased greatly because we were interested not only in integrated, but we were interested in some time resolution as well, and measured ozone as well. For VOCs, volatile organic compounds, and volatile aldehydes, we looked at 31 individual volatile organic compounds. These were chemicals of indoor and outdoor origin. We did more limited because this is more expensive measurements. We did, for each system, 2 to 4 days of 24-hour integrated samples. We did this in the summer period. And we did this for each of the 3 systems that had a VOC removal technology and also for the reference system. So the way we set this up, we were measuring indoors and outdoors, and we were doing this over a long period of time. We had a concern about potential instrument drift and that biasing the measurements. So we had each of these systems, we had an inlet outside and an inlet inside, and then they came to 2 manifolds. Now two valve systems went to the manifolds, to the instruments, and initially, I think it was every 10 minutes, and we switched every 15 minutes, we switched these, okay? So instrument set A was measuring outside first, and then in 15 minutes it got switched to measure inside. So that takes care of any drift or any changes in the instruments because they continue to go back and forth. And then we, through an elaborate analysis, had to put those things together to create indoor and outdoor profiles, bring the instruments together, et cetera. But that enabled us to have very, very careful and we think accurate comparisons between indoor and outdoor. It took a lot of effort to set this up. Conceptually, very cool and easy. In practice, it was not nearly as easy. The key parameter it mentions the indoor-outdoor ratio. I'm going to be showing you some plots that are going to have log scales. The reason we use a log scale is because the indoor-outdoor ratio looks the same on a log scale as the absolute concentrations moving up and down. But if you're on a linear scale, then it looks different. So what you see here is on the right-hand side is a log scale, and the left-hand side is a linear scale. And then you're seeing the top would be the outdoor, the bottom would be the indoor concentration. So the difference of those is the reduction, right? So what you see is on the top is a 95% reduction, on the bottom is a 25% reduction. And then on the left-hand side, when it's linear, you see that the thickness of the gap of the band changes as the concentrations change. And on the right, you see that it's constant. So when you look at these log scales, thicker bands mean better performance wherever you are on the scale. So we're going to look at some data here. These plots are a little complicated, but we think it's worthwhile to go through. What you're looking at here is one of the particle size bins, 0.5 to 0.7. You're looking at the top. We're looking at the bottom panel, obviously, where there's data. We're looking at particles per liter, and there's the 2 dashed lines there are 1 hour average data, running 1 hour average. The top one is outdoors. The bottom one is indoors. Indoors is lower, as we've been saying, right? And you can see there's a thickness to the band. Let me go, sorry, wrong way. So we looked at the 1 hour, and then we also took 24-hour running averages. The PM2.5 standards, the shortest duration is 24 hours. So we're interested in the 24-hour performance. And then by having the 24-hour, we're also now looking at the indoor-outdoor ratio. And you see that as particle levels outdoor are going up and down, particle levels indoors are going up and down, but the indoor-outdoor ratio is actually staying pretty consistent throughout that, right? So this is the fundamental performance of the system is that it's removing something like 60 to 70% of the part of PM2.5 from outdoors is being removed for the indoors. We also looked at a shorter term measure. AirB was interested in what happens over sort of short time duration. So sometimes there are spikes outdoors. And it turns out that your home is a little bit more protective from those spikes because the spike outdoors it goes up really high outdoors, but it doesn't come indoors so quickly. You don't replace your air so quickly indoors, so that gets muted a little bit. And we have the indoor-outdoor ratios from the daily highest 1 hour. I'm not going to spend any more time talking about that today. All that's in the report. I just wanted to point out there are these different measures. So just going back, this was the reference system, right? So there's no enhanced pollutant removal. You're just seeing the benefit here of being indoors in a house that's pretty tight. And this isn't the tightest house, it's a moderately tight house. Now, if you go and you actually add some filtration, system D was the MERV 16 filter, you see a much bigger band, right? A much thicker band. And then if you look at your numbers, remember on the reference system, indoor concentrations were 30 to 40% of outdoors. Here they're 3 to 4% of outdoors. Okay, so you're removing 96 to 97%, 96 to 98% of your outdoor particles are being removed of this size bin. Now we're going to jump to, just when you were getting comfortable with that plot, we're going to jump to another complicated plot because, you know, it's after lunch. So this is like the best time to think, right? Look at a really lot of complicated. Maybe we should get up and do calisthenics and get some movement going. So what you're looking at here are these indoor-outdoor ratios for all the systems going across. And we're in the process, we realized a little too late that we really need to organize the systems categorically with different ventilation and whatever. So I'm going to talk you through the results. Clearly you can see some of these systems are way better, have lower indoor-outdoor ratios are better. And so you see that there's some numbers. Now this is a linear plot, but you see there's some numbers that look very, very close to zero. Broadly, if you start looking at where the numbers are, you'll see that the effectiveness was not the same for all the particle categories. So the ultrafine particles were removed at a higher rate than the PM₂.₅, which was removed at a higher rate than the black carbon. So the homes were least protective for black carbon, most protective for ultrafine particles. The best particle removal, those numbers that are very close to zero, was the MERV 16 on the supply ventilation. That was system C. The MERV 16 on the forced air unit was system D. And then the MERV 13 on the mini split, system F, which was operating continuously. And then next is portables with HEPA and the MERV 13 on the forced air unit. So the logical question here is why was that HEPA filter, or system G, not doing better? And there's two answers. Okay, one is under the best case, HEPA is filtering all the particles out, but it's only doing that on a fraction of the air that's moving through. The second thing is the system as we operated was probably undersized compared to what a manufacturer would recommend. There's a very high energy penalty for using these things. We were trying to cut down on that a little bit, we probably went over. So the performance probably would have been a little bit better if we had sized it according to manufacturer's recommendations in its defense, but it still, from our analysis, would not have been as good as some of these other systems. For most of the systems, you see similar results in summer and winter, with one big exception, which is the system B. Now remember, system B, well, I don't expect you to remember, but I can remind you. System B had that ESP, the electrostatic precipitator. They also call it an electronic air cleaner, same thing. That was on the return, and that was operating whenever heating and cooling was needed. Now, we didn't use a lot of heating, both because we're in Sacramento, it's a well-insulated house, and our instruments were generating enough heat that it actually cut a little bit into the heating load, the need for heating. In the summer, we actually set up a separate cooling unit for some of the pumps and stuff, but there's still a big demand for summer cooling. So in the summer, the air conditioner came on, and that meant that more air was being moved over that ESP. So if you look for system B, you see big differences between the red and blue bars. Okay, so the system B was much more effective in the summer than in the winter for that reason. I don't expect, we're not going to go through this table. The table here is included just for the record because this presentation will go online. These numbers will also be in the report, and this is a little easier to read than going back to that bar chart. Removal during outdoor entry to home. So as we discussed, the lowest performance is these 0.3 to 0.4 particles. And a quick note here, the shell actually looked like it was a better filter than the MERV 13 filter. Now that will probably vary with the quality of MERV. Not all MERV 13 filters are the same. So some may be better than the shell, and also as that MERV 13 filter would load, it would probably start to look better than the building shell over time. Okay, but for the experiments we did, the building shell actually looked pretty good. A tighter building shell we would expect to do better. And new homes in California today are probably being built with tighter shells than that house that we looked at. So for the indoor particles, we did the scripted cooking activity. It was a green bean stir fry. I think it was maybe takes about 6 or 7 minutes. That's what happens what you're looking at here in these plots, you're looking at concentrations of things over time. The red or the pink is during the period of cooking. This was for the system, I think this was, do I say which system it was? I think it was system D. This is one of these intermittent systems. So during the first period of time, the system was off. And then in the green shaded part, the system is on. SF6 was we don't use SF6 anymore for experiments. They did this a couple years ago for climate reasons. But it's a tracer, so this is something that's not being removed indoors. It just gives you an indication that the rate at which the SF6 goes down is proportional to the air change rate. So initially, there's just basically it's the infiltration in this case, and then when the system turns on, we are now ventilating at that higher rate, so the SF6 decreases more quickly, and then the system turns off and then on again. So that's why we see the pattern of SF6. Why do we care about that? Because what we're really trying to see is how quickly it removes the particles. So we need to make sure that we separate the removal by ventilation from the removal by filtration. So if you look at these first order decay rates, okay, what you see is in the first period after cooking, the particles are depositing on indoor surfaces, and that's why we see 0.96 per hour versus 0.17 per hour. So that's just a process that happens every day in your home and my home. And then when you turn the filter on, you see very, very high rates of particle removal, 5.5 per hour. Okay, so that means for every hour you're gonna, it's like the equivalent of turning over the air in your house 5 times in an hour to get dilution, or in this case, removal. And then when you turn the air handler off, the filtration off, you get, again, a lower rate, and then you turn on again and get a higher rate. So for the cooking particles, what we looked at is for the hour after you cooked, I think it was starting from the time that we finished cooking, what was the concentration of particles in the home? For the reference condition in this case is we cook and nothing's on, okay? Because there's lots of time when your forced air unit's not on. The reference condition, though, there is an exhaust fan on. So the continuous exhaust is happening, but nothing else. So then that's the as tested. The white is the as tested. As tested is this, each system was operated as we've been discussing. So the intermittent systems are operated for 20 minutes of every hour. The continuous system operate continuously. So systems A and B look about the same as the reference, right? These were the supply systems. Okay, so the forced air unit's not on. Supply system's not doing anything for indoor particles. The building shell is not doing anything for indoor particles because they're already inside, right? So there's just not a lot of removal there. System D had a little bit of benefit. These are the white bars. System E is a little bit better. System F was the real winner. That's because it's on continuously. And then system, again, D, E, they didn't do as well because of the way we said, we kind of did a worst case. We said we're going to wait to turn the system on until after 40 minutes. So it was the 20 minutes was in the last part of the hour. But what you notice is when you operate the systems, the dark bars you get substantial removal. So this is saying, hey, if you have that filtration system built into your house and something happens, now for cooking, what we really recommend is you use a venting range hood to get the particles and pollutants out of your house before they mix into your house. It's much more efficient. But there's lots of sources of pollutants that happen in your house. something happens, maybe you burn some toast or you do something else, and you say, uh-oh, and I have these particles, what do I do? If you have these things built into your house, you can flip them on, and this gives you an indication of how much benefit you get from turning the system on, and you see you get some really significant benefits. System B, for example, with that ESP, the ESP works really well, right, to remove particles. So if you run it continuously, you remove 75% of the particles. System D, likewise. Okay, it didn't work as well when it was only on for 20 minutes of the hour. At the end, running continuously, it works really well. I'm going to, in the interest of time, I'm going to actually skip this slide. Don't look at the details. The key message to this slide, though, I'm not going to skip it entirely. I'm going to say the key message, which is there's two pieces of relevant performance information with filtration. One is how effective is the filter at removing particles from the air, and this is true of air cleaning too, something from the air that's moving through it, and then how much air are you moving through it, right? So in some of these systems, they were very effective at removing stuff from the air when it moved through, but they were just not set up to move enough air through them. Ozone, I'm not going to spend a lot of time. Ozone was very low inside. In almost all cases, the ozone levels were below the quantitation limits of the instrument, so we saw a very substantial ozone removal. So that meant that we really didn't distinguish any of the systems, like some of those some of the systems were designed to remove ozone. We couldn't see because the shell itself was removing so much ozone, and it also deposits indoors. So a low air exchange rate, a tight building shell, you're going to remove a lot of ozone. That's all I want to say about that. VOCs. So as commonly happens, VOC levels indoors were higher than outdoors. This actually surprised us somewhat because this was basically an empty house, right? So when you bring your stuff in, you bring a lot more VOCs. But even in this basically empty house, the VOCs were 20 times higher indoors than outdoors. And a big chunk of that was formaldehyde. We looked at VOC removal. The way we looked at it is what was the difference in the VOC concentration inside the house when we were operating the system that had VOC removal technology compared to the reference. So we're making an assumption here that the VOC levels are more or less consistently and constantly being emitted. So the VOC emissions are relatively constant. And we think it's a reasonable assumption. The environmental conditions are relevant here. If it's hotter outside, then VOCs that are being emitted from inside the building shell will heat up. Inside the house is the same temperature, more or less, because we're thermal conditioning it. But as we heat up the shell, we may have more VOC emissions. Mostly the conditions were the same. The system that got disadvantaged a little bit in that case actually it wasn't the temperature, it was on the air changes, which is the other piece is that there's, even though we were trying to keep everything the same, just because of different outdoor conditions and different winds and things like that, sometimes the air change rates were slightly different. So if you have a slightly lower air change rate, slightly less ventilation, then your indoor VOCs, you're expecting them to be higher, right? So system C was disadvantaged a little bit relative to the reference, 0.25 air changes versus 0.29 air changes. So we would expect VOCs in system C to be a little higher just because of that. Okay, so when you see in this next slide, for example, that system C actually removed 15% of the formaldehyde, that's probably an underestimate. It probably did a little bit more than that for formaldehyde. And the other two systems had small reductions in formaldehyde. Formaldehyde is kind of the toughest thing to remove of the common VOCs. We look at some others here. Xylene is a element of fuel. Butoxyethanol is that some of those simple green was butoxyethanol. I don't know if it's still in there, but it's in cleaners. D-limonene is in some cleaners. It's also something that comes from wood. Orange oil is D-limonene, basically. And then hexanol is another. And again, you see substantial performance. In these cases, we think the system C is, again, just a disadvantage a little bit. The system C numbers probably should be a little higher in a apples-to-apples comparison. We estimated annual fan energy consumption. So what's the energy penalty of these different systems? The concept ultimately is to inform building codes and standards. And because of our climate goals, we want to make sure that homes are as energy efficient as possible. We're going toward net zero new homes. So anything that has a big energy penalty is going to be a non-starter. So we did look at the energy costs of doing these things. The way we did that is we tried to figure out how much power it takes to run the system, and then how many hours a year will the system be running more than a reference home. So if you're operating your forced air unit for air cleaning, let's say 20 minutes out of every hour, then you're going to operate that a lot more hours during the year than it would operate otherwise. But we need to know how much it would operate otherwise. So we did that through simulation. And the baseline was roughly 800 hours, and then there was about another 2,400 hours that it would need to operate for 2060 operation. And then if it's operating continuously, then obviously it's just operating continuously, so we know that. And then we multiply the operating time by the amount of power. Relatively straightforward, right? Time and then how much power it's using while it's operating. So these are the results. We present these results for a standard permanent split capacitor motor. So this is what's probably in the HVAC systems, the heating and cooling systems in most of your homes and in my home. Newer, it's becoming much more common to have these efficient. There we go. Sometimes called ECMs, electrically or electronically commutated motor. That actually, it turns out, is a trademark term. A brushless permanent magnet motor is another term because it actually describes the motor. These are efficient motors that you can turn down essentially, so you can operate them at different speeds. They operate more efficiently at low speeds. So on the left, you're seeing the estimated annual energy for each of these systems. We're breaking it down into what's in the forced air unit, what's for ventilation, and what's for filtration. So you see, for example, system G, as I said, that was already operating at a lower flow or lower flow than what would be recommended. So that would be the blue and the red. That was already one of the higher ones, and if we had operated it at a higher flow, it would have had a bigger energy penalty. Okay, so we would have had better performance, but bigger penalty. The lower energy ones, the reference, system A, system B, they're all relatively low. System C is a small increment, so that's a pretty efficient, that has a very efficient fan. And the portables, they have efficient fans, and also they're not pushing air through a lot of ductwork, right? So that's why they can use less energy. The big point here is that a lot of the energy penalty is from having that inefficient fan motor in your central unit. If you can put an efficient fan motor in your central unit, you can greatly reduce the energy penalty. And that's what you see on the right. So instead of 1,500, these are kilowatt hours per year, you can cut that almost to a third, okay, or 40% or something. So this is maybe 600 kilowatt hours per year. And I'm looking here at systems D and E, for example. So D and E use the forced air unit, right? And there's a lot of advantage to doing that because you already have that system in your house. You're not having to install any extra motors or anything else. Just put an efficient fan motor in your forced air system, and then you can get a lot of air cleaning benefit from that with a modest energy penalty. Now, we have colleagues, I mentioned Dan and Gavin. If they were here, they're building zero energy homes, and they'll say, well, I don't want to add 600 kilowatt hours a year for that. So they wouldn't like that system as much as they might like, for example, system C or even system B. But I think if you look at most homes, that 500 or 600 kilowatt hours is actually something that you can make up for with a little bit extra solar, or there are ways to accommodate that. It's not such a big penalty. Key results for outdoor particles. There's a lot of words here. I'm more or less just going to read them again. This is just so you have them for posterity. The reference configuration, which was the exhaust ventilation in a moderately tight home, actually reduced concentrations relative to outdoors substantially by about 66 to 73% for PM2.5, 48 to 58% for black carbon, and there we go. The supply ventilation with the MERV 13 yielded slightly. Apologies to a little higher.
Yeah. Okay.
Great. No? Yeah, okay. So the supply ventilation with MERV-13 yielded actually slightly higher particles than the reference. Again, I think if we had continued to watch that as it got loaded, we would start to see that even out a little bit better, maybe even be a little bit better. The one thing we didn't test, you always look back and say, God, I wish I had done this one thing a little differently. I wish we had just done a week with the supply without any filtration. We know what would happen, okay? And that's why we didn't do it, but it would have been good to just have the data to show it. And that is, if you put a supply ventilation system in without any filtration, you will increase your indoor concentrations relative to outdoors substantially compared to the reference system. So supply ventilation without filtration increases your exposure to outdoor particles compared to the reference, okay? And you need a pretty good filter to do as good as the envelope. So I would say, from what we saw here, I would not go below that MERV-13, because if you have less than MERV-13 on the supply, if you're concerned about outdoor particles, you are exposing yourself to more compared to what you would have for a reference case of using exhaust ventilation with your envelope filter. So when you put MERV-16 on the supply or on the forced air unit recirculating, so MERV-16 filter, it almost takes all the particles away, right? You get to very, very low levels. So it's, again, least effective for black carbon, but still 85% for black carbon, 95% for 97, 98% for PM2.5, 97, 99% for ultrafine particles. I don't care whether it's 97, 99. You're taking all the particles out of the air with these things. Do you need that much? Probably not, but it's just you can know that you're getting that effectiveness. The MERV-13 on the mini split we think is an interesting system because I think we're going to see more mini splits, and this shows that even with a MERV-13 you can really have substantial reductions in your particle levels. So we don't know that you need to go all the way to MERV-16, and then the 1-inch MERV-13 didn't do quite as well. The difference between the two MERV-13s may be the filters themselves. Not every filter is the same, and there's some relatively complicated reasons for that, which I can go into if anybody's interested. But also, it turns out that the mini split, system F, moved a little bit more air. It was like maybe, I think it was about 30% more air movement through it. So that may have accounted for the difference as well. Filtration on the supply ventilation provides no benefit for indoor generated particles. It's another thing to consider, which is, if you're only worried about outdoor particles, filtering on the supply is a very efficient way of doing that, but then you get no benefit for the indoor particles. So the advantage to filtering on the return or on the recirculating system is you get both. For systems with intermittent filtration, the reductions for the cooking particles varied a lot with the timing of fan operation, obviously. You emit something now and your filter doesn't come on for 40 minutes, then you're getting no benefit for those first 40 minutes. So when you do filtration on a recirculating system, we actually really prefer, we like it better if it's a lower speed but continuous operation. Because then whenever something happens, you get the benefit starting right away. You don't have to wait around for it. When operated continuously, all the recirculating systems had some substantial benefits for reducing PM2.5 from cooking. For VOCs, filters, and energy, there are available technologies that can cut VOC levels. And we saw that the benzene, toluene, ethylbenzene, xylene, these so-called BTEX compounds, were reduced by all the systems we looked at. You need to consider both the airflow and the single pass removal efficiency. That's true for filters and for the VOC air cleaning. It is possible to get high particle removal rates with low pressure drop filters. So effective filtration does not mean that you have to have a high pressure drop. Filtration on the ducted supply is the lowest energy approach to cleaning outdoor air, but filtration on the forced air system with a standard blower motor, it's effective, but it uses a lot of energy, and using efficient blower motors really can cut down on that. And that concludes the formal part of my presentation. I have some extra slides. We'll see how well I was able to predict or anticipate questions to see if I get to go to any of my extra slides. And if we get through all the questions, for for whoever wants to stick around, I'll show you something interesting and something interesting from the ESP system. So at that point, I think I'm going to move to the questions, and I'll ask my hosts here how they would like me to handle this. Okay, so I think I'm going to read the question and then answer it. I'm going to take just a quick drink. And Hongju, I might ask you to help read it. I am interested in how each ventilation system impacted the house air exchange rate. There is good research showing that an exhaust-only or supply-only system used during the winter with stack effect in operation provide roughly only half the nominal increase in ventilation air when compared to a balanced system. Did you notice these effects? This is a gentleman named Don Fugler, who we know actually very well. He's a very esteemed researcher up in Canada. We saw some variations. Don's research up in Canada, I think the colder it is outside, the more driving force you have for the infiltration part of the ventilation. And as Don points out, sometimes that can really swamp out the mechanical part. In this case, we didn't see anything that was so terribly different in the winter or summer as a result of weather variations. So we saw mostly there were, I'm thinking, I don't think I have that in the extra slides. I should have remembered I have, that's not. Yeah, I don't think I have that done. Maybe 20 to 30% at the outside in terms of the variation, high to low on the air exchange rates. Is there another question?
You showed a slide that had a optimal size, particle size for removal, right? Oh, I guess there are high efficiency on the larger size, and then it kind of drops and they pick up again.
Yes.
What are the physical reasons for the smaller particles that are captured better than?
Oh, the very smallest particles?
Yeah, exactly.
Yeah, that's a great question. Basically, the big particles are removed by impaction. So they have mass. So as they're moving through the air, when they come upon a fiber of the filter, let's say it's a fiber filter, for example, or some kind of part of the, some physical part of the filter, the air has to turn around that filter. And the big particles can't make the turn, so they slam into the fiber and they get caught. The very small particles look a little bit like gases. They're moving around a lot, okay? So they call it Brownian motion, okay? So as they're moving around a lot and they're diffusing through the air, moving through the air, so then as the air mass is moving through that filter matrix, okay, they're just, as they're moving around, they will move into the fiber, okay? So the more things that they come close to, essentially, as the air is moving through, the more chance they have of getting removed. So those particles, if you go into a house, if there's a very high surface to volume ratio in the house, the ultrafine particles will get removed much faster because there's just more surfaces, more materials that they can happen to hit as they are moving around.
But that was was a function of size and also velocity, right?
So the impaction, the larger particles for sure, both of those are impacted by velocity. And the way that larger particles are impacted by velocity is you get some advantage by throwing them harder at things. But then as you move stuff through the filter faster, the smaller ones have less time to hit things as they're moving through the filter. Okay, so velocity is an important factor.
So the curve would shift if you had different temperature, right?
Different temperature, yeah, it will probably depend on temperature, it will depend on velocity, yes, for sure.
All right, okay.
Yeah.
Hi, Brett. Jeff Williams from the Research Division. a question about ozone, which I noticed very low inside as expected, but you mentioned that in your extra slides that you did see ozone produced by the ESP, is that correct?
Yeah, you saw that as I was flipping through, is that?
I was wondering if you could talk a little bit about that.
Yeah, so that's what I have here, right? So this is the ESP, and if you look closely, the gray is the 1 minute data, and the black line is the 1 hour. The black line is the 1 hour data. So if you look closely, you see there's this kind of sawtooth pattern at the bottom on the gray there, and what that is that's the air handler cycling on and off during cooling. So what you're seeing is if you look at the times on August 1st in the late afternoon, okay, what you're seeing first actually is you're seeing, let me just get this 12 o'clock right. So the late afternoon, you start seeing particles are going up inside, and then you start seeing the gray as the system turning on and off. Let me just get to the next picture, it's a little easier. Let me go one more here. Oh, I know, this is, there. I had that backwards actually. So it's the early afternoon. So what you see happening is when indoor particles are going down, it's because your cooling system is on, so your ESP is operating. So kind of all afternoon your system was operating. There's a blue band there. And you see when your system's on it's basically on continuously through the afternoon, your particle levels go way down, which is what we'd expect. And then in the evening, it starts cycling on and off. And every time it cycles off, the particle levels go up. And then it cycles on, and the particle levels come down. Great. And that's why the ESP was more effective in the summer. Now we add the ozone. Now you see the ozone was also highest in the afternoon outside, highest in the afternoon inside, okay? But the telltale sign is every time the system, the forced air unit cycles on and the ESP comes on, we see ozone in the house. The red goes up inside the house every time that the system goes on. The system goes off, the red starts to go down again. Why? Because ozone's reacting with all the surfaces. Even in this unfurnished house, there's a pretty substantial indoor ozone removal rate. And then every time, again, the system goes on, it goes up again. Now, these ozone levels are not very high, right? So even in the afternoon, the system was running continuously. This was one of the few times where we got above the quantitation limit. So you saw a lot of times the ozone was below 2, or maybe hanging around 1. Okay, and that was probably 1 plus or minus 1, again below the quantitation limit. But in this case, you see when the system's on all afternoon, now we're getting up to a solid. It's whatever. It's I think 20, 30, 40, 70 ppb outside, and it's 10 ppb inside. Now 10 ppb is still pretty low. Okay, so I don't know that this is. I'm not going to start saying this is a health hazard. Okay, but it is producing ozone, so something to be aware of, and something that that we would like to see the manufacturers make sure that there's no excess ozone coming out of their products. But these are certainly relatively low levels, but we can see them. Oh, another question from the Google. This is from Henry Slack. Hi, Henry. With all this great research, are you changing anything about your home's own HVAC? Well, it's interesting. We live in Oakland, California, in the delightfully moderate climate of the Bay Area. We don't have cooling, so we're hoping that we can reverse the worst of the climate change, so we won't have to have cooling. We do use our heat in the winter, but we actually open our windows quite a lot. And we prefer the outdoors. It keeps the house nice and dry. Obviously, we close it when it rains. So I haven't changed anything. The one thing we do in our house substantially is if we know we're using some kind of a particle source, let's say we're lighting candles for a holiday or something, then we will increase ventilation. We'll open windows. We'll turn on exhaust fans. and or operate portable air filtration units to reduce the particles so that we can still enjoy the beauty of the candles for the holiday, but not have to breathe in the high concentrations of the particles that come with them. And, oh, right, so the other thing, of course, is the range hood. Yeah, we definitely religiously use our range hood in the kitchen.
Hi, Brett. Thanks for the great study. That will be really interesting to see how that changes our building design practices and everything. In terms of outdoor pollutant sources, did you get a sense of how big the sources were, say, compared to normal, and how much reduction you got? I saw where BC was reduced, like 40% or something, not as much as PM. And
well, no, BC was reduced quite a lot, actually. Okay. The systems, there was less.
I guess the question is, why was that less than the PM₂.₅? Is that just different size?
It's the size.
Chemistry?
Yeah, the black carbon is sitting at that size that's hardest to remove. And there are some of the PM₂.₅ mass is there as well, but a lot of the mass is slightly bigger particles, let's say, 0.3 or 0.4 and above. And the black carbon sitting there, in somewhere in the 0.1 to 0.3 range, so it's in that hardest range to remove.
It seemed like the indoor levels were down around 1 microgram per cubic meter for PM₂.₅, somewhere fairly low.
Yeah.
And the outdoor, was maybe a bit higher. So it seems like you didn't have a strong outdoor source signal. Didn't seem like it was that.
It varied. We definitely saw some. We didn't see crazy high outdoor particle levels. We have no reason to suspect that these results are, very substantially biased by the outdoor particle levels that we saw. The particle levels we saw were particle levels that are encountered. If there was a nearby wildfire or something like that, then it's going to look different. But it's going to look different in part because the particles are going to be different, so the size distribution is going to be different. But I'd say I feel confident that these results are robust and would be applicable to even cases like a wildfire. It will give you a pretty good indication of what you're going to get in terms of particle removal. The difference being, if it's a wildfire, you're going to be replacing your filters not every 6 months, but maybe every week or something, right? You're going to much more frequently. I don't know what the recommendations are, but it's you would have to do it more frequently.
Just one follow-up question. Sacramento has a big wood smoke problem, PM problem in the winter, but it didn't look like you saw much of that during your testing. Was it in the early winter or fall? When
it was in the we had some in. We didn't see terribly cold weather. We saw some, but it was in the first winter was pretty mild actually, and then the second winter, and it was an early spring, and then we did fall winter. Started maybe in October, late October, end of October through December, through Christmas more or less. Stopped before Christmas. And we had some cold days, but it's Sacramento too, so we didn't catch any really cold days. Yeah, oh, great. And I'm waiting for somebody to ask me about recommendations. So if anybody wants to know about recommendations, I have them. The two plots on the slide 34 show air exchange rates with best SF6. Okay, two plots on slide 34. One more, sorry. Show air change rates with respect to SF6 and PM₂.₅. During system operation, the derived air change per hour values differ. Could you speak to the difference? Is ACH species dependent? That's from Patrick O'Keefe in the Lab for Atmospheric Research at Washington State. So the SF6 is the air change rate. The PM₂.₅ is the PM₂.₅, a combination of air change and filtration and also deposition. So in that first period, what we see is that the system was off. Again, I believe this was system D. So it had intermittent ventilation. So we saw moderately high infiltration-driven ventilation of 0.17 per hour. And then we saw much higher PM2.5 losses during that time, which is accounted for by deposition, essentially. So that's the difference. The difference between 0.96 and 0.17 is deposition. And then when the unit came on, the intermittent supply fan turned on, so we see higher outdoor air change rate. That went up to 0.7. And then we see this substantial filtration at a much higher loss rate. And that's from the filtration. That's the 5.5. Any more questions there? No? Okay.
Coming right.
Printer is printing fast. This is great. One of the fun things about this is you get questions from people you know. So, but even if you don't know me, please send questions in. Your slides mentioned that the air cleaners did not do a good job reducing formaldehyde concentrations indoors. Can you talk about this? So they did they helped, okay? Air cleaning is not our recommendation for how you reduce formaldehyde. Actually, I can give a shout out here to Peggy Jenkins with Tom Phillips. Actually, I think was very involved in this too. But this is the California Air Resources Board, and they didn't pay me to say this. They did something that will, I think, result in more exposure reduction for formaldehyde than anything in years and years, which is they passed an air toxic control measure that reduced formaldehyde emissions from manufactured wood products that go into building homes. Now, this was the regulation was allowed as a way of controlling formaldehyde outdoors, which is a problem outdoors. So there are laws against that are promoting formaldehyde reductions outdoors. It just so happens that it also really helps reduce exposure inside your home where there's a lot of these manufactured wood products. Okay, so the source control and the formaldehyde by far the biggest thing. Taking the California's lead, the federal government passed the Formaldehyde Control Act, I think it was called. Did I get that right? Formaldehyde Control Act. So these regulations from California will go into effect nationally at some point. EPA is in the process of trying to figure that out. They're already in effect in California. So all you Californians out there who are buying new homes, you're getting substantially less formaldehyde exposure thanks to the people in the room here. And then for homes that already have high formaldehyde, you're probably going to get a better benefit by ventilation. And just, now obviously you're not going to ventilate when it's in the middle of the summer or the middle of winter, but if you know you have high formaldehyde, the recommendation is to ventilate whenever you can. So when there's nice days out, not big air pollution days, nice weather, ventilate. Maybe when you're away from home, if you can leave a couple windows open, close when you come home, etc. That's much better than the air cleaning. Sorry for the long answer, but I had to, I wanted to get that right. Great. While this study doesn't go into it, can you recommend a good idea for a system in cold climates, also accounting for the energy use? So great question. Certainly, if you're in a cold climate, the benefits of an HRV, a heat recovery ventilator, become much greater. So if you want to do that supply filtration, where you know supply ventilation, a lot of people want to kind of know where your air is coming from. You can use an HRV with a filter. Certainly, the systems where you're doing the filtration on the central air handler. If you're in a cold climate, depending on how efficient your home is, you might be operating your air handler or your forced air unit much more for heating. So then there's less extra cost for putting the filter on that unit. So those are all good options. A lot of late questions coming in. Please keep them coming.
While we're waiting for printing here, I wanted to say thank you to you and your staff for all the hard work. I know you put in so many hours, day and night, to get this study done. I did want to ask about something that you didn't present, but I know it's in your final report, and it surprised me. You made a few measurements of the airflow resistance for some of the high efficiency filters, And I was surprised that it was much lower than I expected. Can you comment on that? I don't know if, don't mean to put you on the spot, but if you remember,
Yeah,
I think it was very low
I mean,
percentage.
the key point here is that there's definitely reluctance in the industry to put high efficiency filters in because there's a concern that it will increase pressure drop in the system, and then that can lead to all kinds of problems. In most cases, and that's because a lot of the practitioners who know something about this go out and see systems that are very poorly designed, okay, and already have too much pressure drop. So you're already using a lot of energy to push air through or pull air through returns that are undersized, through ductwork that's undersized. So there's this general reluctance. The problem really is not with the filters. The problem is with the crappy systems that the poorly designed systems that people are putting into homes that have much more pressure drop than they should. So it's very possible to create low pressure drop ductwork. People do it. Dan and Gavin do it all the time. And then when you do that, then your filter doesn't matter. And then it's also very possible to get low pressure drop filters. So the pleated filters, they look like they kind of, they're pleated, so they have these little folds in them. In general, they're better. In general, if you go with a thicker filter or a deeper filter, so a 4-inch or 5-inch or 6-inch filter is going to have less pressure drop in most cases with the same MERV rating. So a 4-inch MERV 13 will, in general, have less pressure drop than a 1-inch MERV 13 because you're spreading the collection surface over a larger area with those pleats. And the deeper it is, the more area, so you can have less pressure drop for the air to move through that matrix, essentially. So yes, we were pleasantly surprised that a lot of the filters had low pressure drop, and you know, we don't want people to not use good filters for that reason. But we do acknowledge, and we want to caution, if you have an existing system, you're going to want to get a professional in there who understands this and can talk to you and hopefully even explain to you what your pressure drop in your system is and hopefully help reduce that. So the answer there is reduce the pressure drop in the system, low pressure drop systems, low pressure drop filters, and go ahead and get the benefits of the pollutant reduction.
Thank you.
Hi, Tom Phillips again. On the sealing of the shell, there's probably a lot of houses out there in California elsewhere that are a lot leakier and leakier ductwork and so on, and leaks around the filter itself. And how was the leakage around the filter in these particular systems?
So it is it's an excellent question, and I will say that. This house is it was about different terminology you can use. We call it 5/8H50, but basically it was a average tightness house for this era. Homes today are being built tighter. Okay, the ducts are being sealed better. So new homes have standards for how tight the ducts need to be. That's very helpful. And the ductwork in this house was sealed by the high-performance home contractors who put these systems in. So these ducts had extraordinarily low leaks, okay? And then the filter slots that they put in, we were actually interested in, we didn't want the ducts leaking, but we wanted a, sort of a typical filter slot. So they just put a standard package in there, but they did it correctly, okay? And then we did an experiment where we taped around to make sure there was no bypass of the filter. And the standard filter slot, when installed correctly, actually did fine. So that wasn't the problem. A lot of times
fairly snug though. Then.
A lot of times it's just a poor installation, or it's buying the wrong size filter. I mean, there's lots of issues there. I should go back on the filter thing. One of the things that makes it a little harder is it's not always easy to get the filter pressure drop information, right? So it's not like you can just pick up the filter and it's right there on the filter. So some labeling would probably help there, so that the professionals could, or even the homeowners could see what it means. In the same way we want to see meaningful filter ratings for particle removal, we want to see that for pressure drop as well.
And then one question about shell leakage. There's some modeling studies indicate there's a synergistic effect between air cleaning and filtration, where you get an extra bump in removal efficiency of outdoor particles when you have a tighter shell. And so what would you recommend for a real leaky home that's in a high polluted area? Would you recommend both shell tightening and improved filtration and duct sealing?
Yeah, we would. You know, when you have a leaky envelope or shell, the amount of air that comes through there is actually going to increase at the times that are least desirable. So when it's the hottest out and the coldest out, there will be the most air coming into your house. Okay, and that's why for energy efficiency purposes, it's almost always the case that the first biggest bang for your buck measure is to do air sealing, is to reduce the uncontrolled air infiltration into your home. And then when you get past a certain point, a very leaky home this was a 5 ACH50 home, a 20 ACH50 home, probably you get very little benefit in terms of pollutant being removed as air comes through the shell because it's coming through big gaps, right? So the advantage of the air sealing is it's going to improve your energy efficiency. It's going to reduce your energy burden. It's going to probably substantially improve your comfort level, okay? So you'll feel it. And then it turns out will also improve your home's protectiveness from outdoor pollutants, okay? So I'd say number one is you do the air sealing. And then in terms of how you do the filtration, it really depends on the system, right? So if you're an asthmatic and you know the health concern is the more prominent one than for you than the energy one, then I'd say, yeah, put a good filter in and operate your air handler to get filtration, okay? Portables are also a good option. And depending on what system you have, one or the other might be more or less expensive, right? So the better filters do cost something, but if just putting a better filter in your in your central system is relatively cheap. Buying a good portable air filter that's not going to be a big energy waster, so an inefficient one, is several $100s. And then the filters for those are actually more expensive can be more expensive than the filters for your central unit. So it depends on your personal circumstance, but yes, I'd say start with the air sealing and then go to the filtration. The other thing is the air sealing doesn't help any with indoor particles, so take that into account.
Do you have cost information in the report for these systems?
No, we don't. The cost was not a focus, and we didn't want to sort of take random numbers. I have some ideas, but we haven't done a systematic evaluation of that.
So I'll let you read that one, but let me say something about this. It's from Nancy Bernard. She says she would like recommendations. I know, Nancy, I think I know what she's looking for is kind of you looked at 8 different systems, really, and with different parts. I think she's looking for if you could recommend like 1 or 2 sets or systems that you think would be most energy efficient, but also best for removing particles and keeping the indoor air clean. What would you recommend?
Yeah, I'm glad she asked, and thank you, Nancy. For new homes, okay, or if you're doing a major retrofit, et cetera, what we want to see is a tight envelope. Certainly 3 ACH50 is very achievable. Lots of builders, production builders are doing that today. And it's a well-built home, taking care of good moisture management to make sure that you're protecting the inside of your cavities from moisture intrusion. That's very important in a tight home. But let's say a 3 ACH50, a tight shell, so you can control where your air is coming in. The exhaust supply ventilation depends on where you are in the country. For moisture, again, it's a moisture management thing. You don't want to bring, there's some people who don't want to bring moist air through an envelope, through an exhaust system. So when you're in moist places like the Southeast, you tend to see more supply systems. But in terms of how to achieve your pollutant reduction, I would say tight envelope. And then I think it's perfectly reasonable to, I think you want to anyway have a really efficient air handler or forced air. So the blower motor, if you're using a forced air system, you want an efficient motor that has a variable speed and good efficiency of part load with a controller to allow you to do two things, to allow you to run it at low speed, okay? So you could put a good filter on it. You get the benefit all the time when you're using it. You turn it on, and then you maybe the controller, you only have it come on when you're home. You set it like your thermostat, okay? You don't need to filter the air when you're not there, right? You go to work for 8 hours, 10 hours, whatever, turn it off, turn it on a half hour before you come home, and you'll come home to a nice, clean home, and it'll be clean while you're there, and then turn it off when you go back to work the next day. Filtering on the supply is also certainly a fine idea. The one thing I'll say about that is sometimes, depending on how it's configured, the supply filter might be in a place that's not convenient to get to, okay? And then that gets clogged, it doesn't get changed. A lot of times the supply filters, especially if it's on an HRV, are really, really small physically, okay? So you're pushing all the air through a small space, and the filter gets clogged more quickly, and then it stops working because it doesn't pass any air, right? So that's something to pay attention to. In general, it's better to work with really big filters because there's a lot more surface area, they're a lot more forgiving. If you don't change it exactly at the 6 month or a year, and you don't need to change them every 6 months, probably a year is fine, but you don't want to leave it in there for 5 years. And when the filter is in a place you can't easily get to, they don't get changed as often. Two more, okay. So can you supply a recommendation? Can you supply a recommendation for homes that have hydronic heat or ductless mini splits and no forced air system? So the ductless mini splits, basically, if you have a system like that, hydronic heat, so you still need to do some ventilation. So filtering on the supply can work. Again, you get some benefit from the envelope filtration if you have an exhaust system, and then you can also use portables as a supplemental filtration for when you're doing something that requires the indoor filtration. They work very well. They're low energy. Again, it's not that we're disinterested in them. This study was more about kind of new home standards and what we want constructed into the home. But if you have a home like that, you can again do supply filtration and take care of that. And then these homes have ventilation, bathroom, kitchen fans, correct. Okay. In your slides with supply and return systems, have you looked at the effects of closed doors between supply and return connections? When doors are open, the effective area is very large. Doors closed, right. So in this house, we had all the doors open. Closing doors definitely separates parts of the house off from others. Also, two-story houses, okay? If you have a two-story house and it's a home, we were just doing experiments of another type. I don't know if, I won't mention the name because I don't know if he wants to be mentioned here, but it was a call to mention, and his name is Andy Wall. He's a colleague who has a very energy efficient home, 2 stories, it's well insulated, air sealed, okay, and he has a HRV that's supplying and exhausting from both floors. Okay, so he's distributing his ventilation air, he's pulling air from multiple places. In his house, the 2 floors don't mix between each other. Okay, it's almost like each floor is separately communicating with the outside through this ventilation system. He also has a filtration system, so when his air handler is on, there is a little bit of mixing, right? Because it's taking air from multiple places and sending it back out to multiple places. So the point being, in a older home, okay, there's a lot of vertical temperature differences. Hot air, less dense, is going to go up, is going to rise. So in the winter, there's a net flow up. In the summer, there's a net flow down. And even if you have a single-story house, that happens within 1 story, right? Stuff goes to the higher, the warmer air goes up, the colder air goes down, and that drives a lot of mixing, right? In these very energy-efficient homes, you don't see that nearly as much. So there's not as much mixing going that way. And then if you so one of the approaches is to mechanically mix. We didn't study it here, okay? It's a very interesting topic. We treated this as a well-mixed space, but if you are not mechanically mixing and you have a setup that dissuades mixing, then yeah, you have to think about each space that's separated from all the other spaces as its own space, right? So if you're having a bedroom door closed, what's going on in your bedroom is what's going on in the bedroom. So you may have some kind of filter somewhere else in your house, but you're burning a candle in your bedroom with the door closed. You're going to have really high particle concentrations in your bedroom. So if you don't want high particle concentrations in your bedroom, you need to either have some kind of exhaust ventilation or filtration in your bedroom or something like that.
Now we can wrap it up. That was a great presentation, and thank you, Brad. And also thank you for attending this seminar in person and by the webcast.
Thank you.